Okay, if we got a planet in a circular orbit as we've seen previously, orbit of distance r, then the velocity of that orbit is determined by the radius by setting the expression for centripetal force equal to the expression for gravitational force. And we get velocity at distance r, and of course the result there, very easy to obtain by writing out the details of this equation, solving for v, gives us velocity at position r, v of r, is square root of gm over r, big G, big M. Now, if we increase the velocity here, if we're in a satellite, you know, we step on the gas or whatever you do to accelerate a satellite. Well, yeah, what you do to accelerate the satellite is you burn thrusters and burn in the direction of motion. When you burn the thrusters, it doesn't have to be in the direction of motion, but we choose to do that. Then we're going to get some new velocity. And I didn't leave myself a good place to label that, but this is going to be our velocity. I'm just going to call it v right now. I'll probably put a subscript on it later. Well, that velocity is going to be too great to stay in the circular orbit. It's going to take us outside of this orbit. And this is going to occur in such a way that we go into an elliptical orbit. It comes back to the same point. Now, there are arguments we can make that show why you come back to the same point, but what I really want to do is think about the energy relationships in these orbits. So we have this new orbit. This is an elliptical orbit. The planet will be at one focus, and the other focus will be, well, by symmetry, it'll be about here. Let's not worry about the other focus. It's not going to be important right now. Okay. Then the center of the elliptical orbit might be about here. We'll have a distance a from the center of the orbit to this extreme point, and a distance, equal distance a, from the center to this point. Now these points have names. The point out here is called your apogee. And this point is called your perigee. Perigee is closest to the planet. Apogee is the point that's furthest from the planet. I said we want to talk about energy. So total energies. We saw last time that the total energy in the circular orbit, which I'll abbreviate E, circ, is negative 1/2 capital G capital M over R. The energy of the elliptical orbit E elliptic is -1/2 big G big M over A, where A is half the distance between the perigee and the apogee, and you call A, well, you call this distance, the greatest distance between 2 points of the ellipse, the major axis of the ellipse, and you have a minor axis in this direction. And you call half that distance the semi-major axis. So this A is your semi-major axis. And it turns out that it doesn't matter what the semi-minor axis is, or the minor axis. The energy of the elliptical orbit is going to be this. And we see that there's a third energy that I want to leave room for here. Actually, the third orbit I want to look at is just the circular orbit at the distance of the apogee. So you're going to have a circular orbit that comes around like this. So energy of circular orbit 2 is going to also be -1/2 big G big M over A. Big circular orbit out here. Now the potential energies I'm going to have to do just a little something with my notation. Instead of R here, I'm going to call this R sub 0. And that'll make this R sub 0. And it'll make this R sub 0. Because I want to use R in the expressions for potential and kinetic energy, especially potential energy. Okay, potential energy, as we saw by integration previously, at any point where your distance from the planet is R, is going to be negative big G, big M, little m over R. And now, yeah, thought I had a problem. I don't have a problem. Okay. In particular then, anywhere on the orbit R0, the potential energy is this, and the energy, total energy is this, so the kinetic energy is going to be circular. Well, it's going to be the total energy minus the potential energy by energy conservation. Before I get into that, let me draw a little diagram of these energies. Here's energy equals 0. Recall that occurs at infinity because these energies are calculated relative to infinity. Okay, so E would be greater than 0 up here, and E is less than 0 on this side of the line. Notice that all these total energies are negative. So we have, the energy of the circular orbit is down here. It's a negative energy, meaning that to get from the circular orbit far enough away that we never get to come back, we have to have a negative energy here, So we can climb toward infinity, and we're down the hole here, and we're trying to climb up to the ground level, let's say. So we have to increase our energy to get from this up to energy 0. Okay, the energy of the elliptical orbit, where A, at least the way I've drawn it here, is greater than R. Well, the reciprocal of a smaller number is bigger. The reciprocal of a bigger number is going to be smaller. Since A is bigger than R naught, follows that this energy is less. Well, let's go back. I didn't say that quite right. Okay, the magnitude of this energy is greater than the magnitude of this energy because A is greater than R naught. Dividing by the bigger number gives you a smaller result here. Now these are negative, so in a sense then, this is a bigger negative than this is, meaning that this energy on the diagram the energy of the elliptical orbit is closer to 0 than the energy of the circular orbit. It's a negative number with a smaller magnitude than the energy of the circular orbit, and you want to sort that out and get that straight because it can be pretty confusing. Okay. Now, potential energy anywhere is this. So, for the circular orbit, and we saw this before, this is the energy of the circular orbit minus the potential energy at distance R naught. And that turns out to be plus 1/2 big G, big M, little m over R naught. Now we did this one last time for the elliptical orbit. The kinetic energy, okay, in the circular orbit the kinetic energy is always the same because R naught doesn't change. In the elliptical orbit, kinetic energy at excuse me, distance R, where R is some distance between the distance of the perigee, which is R naught, and the distance of the apogee, which is, I mean, you can work it out. This distance is 2a, this distance is R naught, so this distance is 2a minus R naught, and yeah, well, there you have it. But we're not interested in that. Those are the limits on the distance. And I'm going to write those down. But so this is a total energy in the elliptical orbit minus potential energy at distance R, which is this. But of course the energy of the elliptical orbit is this expression, and you know what? Didn't write down the little m in these expressions, so we've got to have that in there. Hopefully that didn't confuse you, but actually hopefully it did, because that means you're paying attention. But yeah, that was a mistake on my part. Okay, so energy of the elliptical orbit is this, and this turns out to be, since the energy of the elliptical orbit is negative 1/2 with this expression over the a. If I write that expression in here, I'll have the negative 1 over 2a. I can factor out the big G, big M, little m, and I'm going to get big G, big M, little m times 1 over r minus one over 2a. Now I'm thinking about that, making sure that that makes sense. And it certainly makes sense because A is, in the sense that A is already bigger than R, and 2A is even bigger than that. So this term is going to be a lot smaller than this term. So this is going to be positive, as kinetic energy has to be. Somehow I don't want to have a 2 in front of that A. But looks like I've got to have it. Everything here is nice and consistent. Okay, so the elliptical orbit has this kinetic energy at a distance r. And consistent with what I said before, r for any point of this orbit lies between r0, which is the distance it has here at perigee, and 2a minus r0. 2a, subtract the r0, and you have this distance. Okay, now at r0, again, clearly this is a lot bigger than this. The denominator is smaller, so the reciprocal is bigger. And if this is 2a minus r0, it's still less than 2a. Okay, if r is 2a minus r0, then it's clearly less than 2a. 2a minus r0 is less than 2a. So this is still bigger than this, meaning that you're not going to have a zero kinetic energy. You're going to have a positive kinetic energy at both points, greater here than here. Because of energy conservation, of course, you're going to have a greater velocity here than you have here, because between here and here your potential energy decreases. Since your potential energy decreases, your kinetic energy has to increase. So as you move closer to the planet, as you do all the way from apogee to perigee, you're getting closer and closer to the planet, so that your potential energy gets less and less. Okay, your potential energy keeps decreasing as R keeps decreasing. Because, of course, as R decreases, this much increases, but you take its negative and it decreases. So your potential energy decreases as you move toward the planet, and that's intuitively the way we understand potential energy with a gravitational field. Formula gives you the same thing. Potential energy is decreasing, so your kinetic energy is increasing. Now you start using up some kinetic energy and come back here to whatever your kinetic energy was here when you started. And then you keep doing the same thing over and over again. Now, in order to achieve the circular orbit I talked about earlier, circular orbit that can be attained by taking your velocity here, and this blue velocity vector is shorter than this one. Why? Because we're losing kinetic energy. We're gaining potential energy, losing kinetic as we move from here out to here. The velocity here is not sufficient to maintain a circular orbit. We need a velocity boost. So let's say we increase our velocity sufficient to and maybe I want these things to be more consistent, so I'm going to make this a little shorter. Sufficient velocity now to boost us into a circular orbit. Not a very good circle, but better than I feared it might be. It should be level down here. And too close to the board to do it right. So this is a circular orbit. Okay, this elliptical orbit, if I can talk, elliptical orbit again, total energy, -1/2 big G, big M, little m over A. And in your circular orbit, call that circular orbit 2. Again, you have total energy, -1/2 big G, big M, little, big G, big M, little m over A. And that doesn't completely make sense because you've got to add energy here. At this point, your total energy was E elliptical equals this. If you add energy by increasing your velocity, that just can't be right. Oh, wait a minute. Okay. And it isn't right, and this wasn't right. A is not the orbit of, or not the radius of this new circular orbit. The radius of this new circular orbit is 2a minus r naught. And I mindlessly wrote this down as if the radius of that orbit was going to be a, which is not the case. Okay. Orbit is around the planet. Again, you got distance 2a here, you subtract distance r naught here. So let me correct this. And that removes the contradiction that came from my mindless expression over here. Okay. From this, we can figure out the speed we would need for this orbit. And that's very straightforward. You just subtract the potential energy in this orbit. Well, let's write it out. We'll call that KE2, kinetic energy of the second orbit, is the total energy of the circular orbit 2 minus the potential energy at distance 2a minus r naught. And that's going to be -1/2 big G, big M, little m over 2a minus r naught minus the potential energy at this distance, which is negative big G, big M, little m over 2a minus r naught, which is going to end up being just I have a good place to write it, which equals just positive 1/2 big G, big M, little m over the quantity 2a minus r naught. Of course, if you want the velocity in this orbit, you can easily set this equal to 1/2 mv squared, find the velocity. So now we have a model where we can find the velocity of any circular orbit. We did that previously. That's very straightforward, set these things equal. We can boost this into an elliptical orbit of any desired dimension by adding enough energy. And once we have that orbit, we can calculate the velocity at any point from the kinetic energy. Here we have it. Just set this equal to 1/2 mv squared. And then we can figure out the total energy of the circular orbit we would get up here. And if we want the velocity, we set that equal to 1/2 mv squared. And this is kind of a handy thing. This is the simplest way to get from one circular orbit to another. So if you're driving around space, or more realistically, because you don't drive anyway, but if you're orbiting a planet and in a circular orbit, and you want to achieve another circular orbit, the simplest way to do that, maybe not the most efficient, maybe not the quickest, the simplest way, the easiest to understand, is to simply boost yourself into an elliptical orbit that takes you out to the distance you want to be from the planet, and then at some point, well, at some time when you get to that distance, to the perigee of that, the apogee. I know the difference. Having a strange day here. Okay, you get to the apogee, and you boost your speed sufficient to get to the circular orbit by adding the proper amount of energy. Now, any way you go from this circular orbit here to this circular orbit here, it's going to cost you the same amount of energy, because the total energy of this orbit, total energy of this orbit are different. Okay, this orbit has a higher total energy than this orbit. So you're going to burn the same amount of fuel either way. There are other ways to change the orbit. You can go into just keep adding energy. You can go into an elliptical orbit with a little greater apogee and boost into another elliptical orbit with a greater apogee and approximately spiral out to this orbital distance. And if you're not sure exactly what needs to be done, it might be better to do it in smaller increments. Now, I'm no orbital mechanic and I'm no rocket scientist, and I don't calculate transfer orbits. That can get extraordinarily complicated, and I've never dealt with those particular calculations. And we don't want to deal with them in this course either. Just the principle, what happens to the energy. This allows you to answer a lot of really kind of important questions. Okay, well, that's just kind of an overview, an energy overview of orbits, circular and elliptical, and maybe how you get from one circular orbit to another, one strategy for getting from one circular orbit to another.